idea of deep declarative networks came out of a technical challenge that we needed to solve within the Humans Action and Robot project, where we were doing activity recognition. We wanted to have a model of the activity be built into a deep learning system, and we didn't know how to do that. So we worked on the technical aspect of it, and we solved that problem. And of course, at the time, we didn't think of anything more than that. We were just trying to solve activity recognition. It was a couple of years later that we thought, well, we could actually generalize this idea to deep declarative networks. And the basic idea is that you take a model that we're calling a declarative model. So you don't specify exactly how you're going to solve the problem, but you specify what the outcome is that you want. You might have a hard constraint for a self-driving car that says that the car needs to stay in the lane. Or you might, when you're doing human pose estimation, have a hard constraint that says that a human's hand can't go through a table. So when you're estimating where the human is, you build that constraint into it. These are very, very difficult constraints to put into existing deep learning models, but we can build them up in a declarative way. And the challenge then is, once you put these constraints into the deep learning model, how do you enable that model to learn in an end-to-end fashion, which is what deep learning is fantastic at doing. And so that's sort of the technical challenge that deep declarative networks solves. And now that we have that technical challenge out of the way, we're starting to apply it to a whole lot of different application areas beyond activity recognition.
So the work that I've been doing most recently has been on camera localization, which is working out the sort of position and orientation of a camera, given that you have a single photo and a 3D model of the location. So you might have, say, like a point cloud of the building that you're in, for example. And so there's a lot of things that you can do with that, and what we've been looking at most recently is using deep learning to extract the sort of patterns from the data to work out what points in the image correspond to points in the 3D world, and then using more traditional computer vision mathematical techniques to, from that, get the position and orientation of the camera. And so my work is really combining the two and finding out ways to do that.
The other area we're applying it to, and we hope to have work out very soon, is in making models more robust. There's been a demonstration of the brittleness of deep learning models called adversarial attacks. And so the idea is that you take an image and you modify that image ever so slightly, so it's imperceptible to a human, but it completely breaks the deep learning algorithm. So without the modification, you might give the deep learning algorithm an image of a dog, and it says with 99% accuracy, with confidence, there's a dog in this image. And you just modify a few of the pixels, so it still looks like a dog, but you give it to the deep learning algorithm and it'll say with only 5% confidence it's a dog, and with 99% confidence it's something else. So this is a problem if you're going to deploy deep learning algorithms in the real world. There have been demonstrations as well where you can put a sticker on a stop sign, and a self-driving car would fail to detect that there's a stop sign there. So it's a little bit of a concern. We think with deep declarative networks, among other advances that people have been making in defending against adversarial attacks, that we can make these models much, much more robust.
The solution really crystallized around some other more theoretical work that we've been doing in the center with Steve Gould. So this is about differentiable optimization layers. So putting optimization inside your network. And this actually lets you combine the sort of more traditional computer vision techniques of optimization, modeling, and sort of the mathematics of how images are formed, and putting that inside a network and still being able to learn in the way that is very popular at the moment.
Deep declarative networks is still a very new idea. It's, as I said, we had inklings of the idea back in 2016, but it's only really been 2019 and 2020 that we've pursued it as a separate research idea, and where other groups around the world have started to get involved as well, so Stanford and CMU in particular. There are a bunch of challenges that still need to be addressed. One is to demonstrate the usefulness of deep declarative networks in a whole lot of different application areas. With deep declarative networks, there's some hope that we can start having mathematical guarantees. So we will know that under certain assumptions, we can guarantee the performance of the model. And I think that's something that's very important for particularly safety critical systems. If you're going to have these models running in self-driving cars or even in decision-making processes to help in medical or other areas, you want to have confidence that it hasn't just been tested on a set of data that somebody's collected, but it also has some rigorous mathematical guarantees as well.